So the natural log function, written as ln of x, please don't call it line or ln of x. Yes, it's ln, but call it the natural log. No one calls it line or ln. Some people say ln, not ln, just ln. But honestly, just call it natural log. All it means is a logarithm with base e. Also called the natural base. That's why it's called a natural log. Why is the number e considered to be the most natural base to use? Again, it has to do with calculus. Just take our word for it for now. But that's a number that's bigger than 1, so it's this picture down here. The exponential of base e opens like this, so the natural log function opens like that. Okay, so can you find the domain of f of x equals negative natural log of x plus 1? Graph it, determine the range, determine the vertical asymptote, find the inverse function, define the domain and range of inverse function, and graph the inverse. So do what you can. We'll work through it piece by piece, but try to get as far as you can into this on your own. Okay. So the input of a logarithmic function has to be positive, but in this example, the input was x plus 1. So x plus 1 must be positive, so x must be bigger than minus 1. So the domain is everything bigger than minus 1. So to graph it, we need to do two things. We need to shift left by 1 and do a reflection. It doesn't actually matter which one you do first. They've done the reflection across the x-axis and then shifted left by 1. I would generally do it in the other order, but whatever. So there is our graph, the picture on the far right. So what's the range? Now the range of a typical log function is all real numbers. And this just got reflected, but that's still all real numbers, and a horizontal shift will not affect the range. So the range is still all real numbers. The vertical asymptote did get shifted, though. The reflection doesn't care, but shifting left by 1 means instead of x equals 0 being the vertical asymptote, I move that left 1, and now I have x equals negative 1 is the vertical asymptote. Now let's try to find f inverse. Okay, so what you do is you take your expression and you switch your x's and y's. So now I have x equals negative log of y plus 1. Now I need to solve this for y. So let's isolate the log by multiplying both sides by minus 1, and now I'm going to convert it into an exponential. And remember, this is a logarithm of base e, so I have an exponent, an exponential expression of base e. So this converts as e to the minus x is y plus 1. Now I can solve for y just by subtracting 1, and there we have it. So there's our inverse function, e to the negative x minus 1. Okay, the next part was find the domain of f inverse, but we already found the range of f. Okay, so we had f inverse was e to the minus x minus 1. We could ask what's the domain of this, what's its range, etc., but we really don't want to, because we already know the answer. The domain of the inverse function will be the range of the original, which we already determined was all real numbers. Similarly, the range of the inverse is the domain of the original, which we already determined in part C. It's everything bigger than minus 1. This is a really common question we like to ask, like, here's a function, find its domain and range. Now find the inverse. What's its domain and range? And we take great sadistic joy in watching students struggle to do all the work again when they didn't have to. Okay? If you know the domain and range of the original function, then you switch them to get the range and domain of the inverse function. Okay, to graph it, to graph the inverse function, there are a couple things you could do. You could start with your normal exponential and do various reflections, or you could just take the logarithmic curve, the blue one, that we already had, and then reflect it across the line y equals x to get the exponential, the green one. Alternately, you could just plug it into a calculator. Drawing curves is not something we're in the habit of putting on exams because your calculator will just do it for you. It's a handy skill to have. The reason being, if you are quite comfortable doing this by hand, when you plug it into a computer, if you accidentally made the wrong exponent or something, so suppose you just plot this instead, because you forgot to make the exponent negative. it's going to look radically different. And if you're really comfortable doing this by hand because you've practiced a bunch, you might recognize the picture doesn't make any sense. And then you'll be like, oh, I must have made an error. If all you've ever done is use your calculator and just shrug and believe it's working and never understand why, if you make a dumb mistake, I shouldn't say dumb, a totally understandable, silly mistake, I forgot a minus sign, you won't notice that the answer the calculator is giving you doesn't make any sense, and then you'll get the problem wrong and you'll never know why it was wrong. So practice this stuff by hand. It really helps even if you are allowed to use a calculator. That's my point. So that was the natural log. A really common base for exponents and logarithms is 10. So if you don't see the base written at all, it's just log. The understanding is that the base is 10. What I would point out is this is in physics and engineering. This is common. Caution. In upper level math, come on, pen, get back there. In higher math courses, log x usually just means the natural log. So this book and most like Calc 1 or Calc 2 books will use the convention that if you write logx, what you mean is base 10. If you start going further and further into math, we never use any base other than e. Like, I'm being quite honest, like there is no reason to use a logarithm of any other base in any problem at any time. Okay, the natural log will do everything you want, and so we just use that. And if we write log, we mean the only logarithm that any of us would ever use, the natural log. Okay, but in physics, powers of 10 are quite handy. Like if you're working with the metric system, you have grams, but then you have kilograms, and you have metric tons, and these are all powers of 10. And so if you're working with powers of 10, a logarithm of base 10 is quite handy. So this is called the common log. Another one that gets used in computer science and certain applications is called the binary log. So y is log base 2 of x. There's no special symbol for it. It's just the logarithm of base 2 is sometimes called the binary logarithm. So common logarithm, base 10. Binary logarithm, base 2. Natural logarithm, base e. Okay, so let's do some examples. Find the domain of the common log function, f of x equals 2 times the log of x minus 2. And notice that the base isn't written. It's just written log. That means base 10. Graph the function, determine the range, find the inverse. It's all the same stuff as the previous problem. So take a moment, try to work this out, and then we'll work through it. Okay. Hopefully you paused and tried to do as much as you could. So I need my input to be positive. Now my input was x minus 2, so therefore x minus 2 needs to be positive, or x needs to be bigger than 2. There's your domain. To obtain the graph, we'll do a couple of transformations. Okay, so first we'll shift 2 to the right. And once we've shifted 2 to the right, we will stretch vertically by a factor of 2. So now the range is all real numbers. The horizontal shift totally did not change the range, and stretching by a factor of 2, if you started with all real numbers and then I stretched to be twice as much, that's still all real numbers. The vertical asymptote, however, did get shifted 2 units to the right. So the vertical asymptote is x equals 2. To find the inverse function, we just switch x and y. To solve for y, I want to get the log by itself, so I divide both sides by 2. Now I convert it to an exponential, remembering that this was a base of 10, and solve for y. So there's my inverse function, 10 to the x over 2 plus 2. What's the domain and range of the inverse function? The range and domain of the original, which we already found. And to graph it, again, you could do it through transformations, or you could just reflect the original curve. So here is my original curve, which is quite easy to do the reflection of, because it didn't go through that line y equals x. So it was this one is a little easier to just draw as a reflection. Also note the vertical asymptote of x equals 2 got reflected to be a horizontal asymptote of y equals 2. That's another handy sort of thing you can draw. As much as it looks, by the way, in this curve, this is not a vertical asymptote. Just like this is not a horizontal asymptote. Okay? It's very, very slow growing. It looks flat, but it's not. It is not a horizontal asymptote. Okay, so in this video we'll come back and we'll just keep doing more examples of solving logarithmic equations.